Okay, let's solve maximum profit from valid topological order in a DAG, directed acyclic graph. And so the idea is that we have a DAG and we also have an array score. And the idea is among all the valid topological orders, among all the valid topological sorts, we want to know which one maximizes the overall profit, and the formula they give us to calculate the profit is the product of each node score and its position in the ordering, right? If you are among the first ones in the topological order, you have a low sort of multiplier, but if you're at the end, you have a high multiplier, right? So for example here, there's only one valid topological order, 0, 1, so this will have a multiplier of 1, this will have a multiplier of 2, and this has score of 2, this has score of 3, so the answer is 2 times 1 plus 3 times 2. And here we have an example where we have two different topological orders, two valid ones, 0, 1, 2 or 0, 2, 1, right? And we can see that 0, 2, 1 is better because 1 has a score of 6, so we want to have it as late as possible in the topological order. And this is indeed what they say. And the first thing you might think about is to use greedy, right? You want to keep the high scores for the latest stages of your topological ordering. So whenever you have a choice between a few nodes, you always use the lowest scores, right? That's a very, very sort of intuitive way to think about it. Unfortunately, it doesn't work because sometimes you want to use a high score to unlock some low scores. And I'll give you an example, right? So for example here, I have 4 nodes, and in the nodes I've drawn the scores. And so if you do greedy, you'll start with 9, thinking you'll use 10 later, and because you use it later, you'll have a better score, right? Because the thing you multiply the score by increases every time, right? So you either use 9 first, so 9 times 1, plus then 10 times 2 because you have to, and then you would use again the lower one, 1 times 3, plus 2 times 4, and that's a plus, sorry. And that's 9 plus 20 plus 3 plus 8, that's 11, that's 29, and that's 40. And if you had used 10 first, you would have something like 10 times 1 plus 1 times 2 plus 2 times 3 plus 9 times 4, that's 10 plus 2 plus 6 plus 36, 18 plus 36, so that's 54. So here you can see that by using 10 you unlock 1 and 2 and you can use them, and you can use the times 4 on the 9, which is great and yields a better score. So that's why greedy doesn't work. And the second thing you might think about is just to brute force all the topological sorts that are valid, because n is quite small, n is 22 at maximum, so you might think that's low enough. Unfortunately, if you think about a graph that does not have any edges, you only have 22 nodes, basically all the permutations of nodes are valid topological ordering, and that's 22 factorial, right? You have 22 choices for the first one, then 21 choices, then 20, etc., etc. And that's 10 to the power of 21, and there's no way your computer can make that many operations in less than a minute. So that's also out of the picture. And so the way we'll solve the problem is that we will use dynamic programming. And to use dynamic programming, we need to to have some sub-problems we need to solve. And here the sub-problems will be the maximum score we can get once we've placed in our topological ordering some subset of nodes, right? So if n equals 4, maybe we're interested in the maximum score we can get if we've placed only nodes 0, 1, and 2, right? And we haven't even looked at node 4 yet, node 3 yet. However, we need a way to represent those subsets, right? Because we want to have a list of integers, right, for this DP array, for example, or a list of lists if it's two-dimensional DP. And the way we'll do this is we'll just use the bit mask, right? And for example, if n equals 4, if I'm saying the bit mask is this, this means node 0 is not in the subset I'm considering, node 1 is, node 2 isn't, and node 3 is. Right, and this is just because this is 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, and 2 to the power of 3. And so I can have an array dp of bit mask, and this will be the maximum score we can get, or profit, I guess, the maximum profit we can get once we've used all the nodes in the bit mask. When we've placed all the nodes in the bit mask in a topological order. Obviously, loads of bit masks will be unreachable, right? For example, if edges is just 0 to 1, then the bit mask 1, 0 is invalid / will never be considered, because that means we have put the node number 1 in the topological order and we haven't put the node 0 in the topological order. However, it's not possible to put the node 1 if we haven't put the node 0, right? Otherwise, this is not a valid topological order. So, although we are having an array of size 2 to the power of n, we won't consider all the subsets, subproblems in this array. We could, right? Usually when you do dynamic programming, you just compute everything. You don't sort of care if it's reachable or not. But here we won't, because this will prune a lot of situations and it will increase the runtime a lot, right? It probably won't increase the worst case complexity, but the average runtime will be improved. And so the first thing we can do is just to initialize our DP array. So our DP will be just a list of integer, and it will be a list of size 2 to the power of n, right? And so that's, we'll put -1s everywhere because initially we don't know what the best value is, and this is 2 to the power of n. And at the end, the result we're interested in is the maximum profit when we've placed all the nodes, right? So this will be 1 everywhere, right? It's also the last element of DP, right? Because the last element is 2 to the power of n minus 1, and this just happens to be all 1s from 0 to n minus 1. So at the end, we'll just return DP minus 1. Now for the initialization, well, what is the best profit we can make if we consider no nodes, the subset of no nodes in our topological order, right? Well, it's obviously 0, so the initialization is quite easy. For the transitions though, as I said, we are going to try and be a bit clever in the way we're doing this, and we'll do something that resembles a sort of BFS. So we know that all the topological sorts, the valid ones, they have at most n steps, and so we'll just go through this graph of valid topological orderings in a BFS fashion, right? So the first, it'll be clear when I write the code, but basically we want to iterate over all the bit masks in a sort of smart way. And the transitions, the first thing we'll do is we'll say for k in range n, and k will represent the number of nodes we have put so far in our topological ordering. And so we want to have a memory of what were the valid subsets we had for k minus 1. So we'll have a variable which is valid subsets, which will be a list of masks really, and the first mask we have is just the empty mask, right? The empty subset, which is just 0 because no nodes are in there. And so we'll iterate over all those valid subsets, all those valid topological orderings, but that only have k minus 1 nodes, right? And this is why I'm saying it's a BFS, right? First of all, we create all those valid subsets with k equals 0, then k equals 1, then k equals 2. And to build k equals 2, we just look at all the k equals 1. And we want to add a node to those valid subsets. So we'll have another loop for j in range n. And this will just be the node we try to add. And the first thing we can check is if node j is already in the mask, we can't add it again, right? In the topological ordering, every node appears once and only once. So if mask and 1j, 2 to the power of j, so basically if 2 to the power of j, the jth bit in mask is already on, then it means that j is already in the sub problem we're looking at, so we can't really add it again. So that's the first condition. And the second condition is we also want to see if j is allowed at this point, right? Because if we look at this example again, we are not allowed to put the node number 1 if we haven't put the node 0 yet. So we need to find a way to code this up. So we could make a function, but the easiest way we can do is to pre-compute. We'll pre-compute this here, and we'll just say, we'll just create a precursors, how can I call this? Necessary precursors will be just a list of integers. And for each node, I just want to know what subset is necessary for me to be allowed, to be added, right? So I'll write the code and I explain. Necessary, not precursor, necessary precursors. And that's exactly it, right? Because whenever we have an edge from U to V, we know that to have V, we need U. And to have U, we also need the precursors of U. And we do not include them in necessary precursors V. And that's okay because we say we need U, and we will never have U without having the precursors of U. So that's okay. And so this will also be bit masks, right? And the idea is this is allowed J. Now it's easy to code. It's just we want to be sure that all the bits here are in mask. So if we just do an AND between mask and necessary precursors, J, we should have this equals to necessary precursors J. And so that's the condition for us to be able to add J to our topological order. And just to recall, mask will represent the valid topological ordering of size K. We want to create valid topological ordering of size K plus 1, and compute the max profit we can make with them. Right, and really the point of iterating through this DP array that way is to avoid going through loads and loads and loads of states that are unreachable, right? Because among the n factorial state, more often than not, most of them are, among the 2 to the power of n states, most of the time, loads of them are unreachable. And so the new mask, now that we know j can be added, a new mask will just be mask or 2 to the power of j. So I should really be pre-computed j bit mask. I should pre-compute this instead of doing this. And so I have the new mask, and I can then do dp new mask equals something, right? And this something will be a max between what there was already here if we got to that state but with a different ordering, or dp mask plus k plus 1 times score j, right? Because k is between 0 and n, the multiplier starts at 1. K is between 0 and n minus 1, and the multiplier starts at 1 and ends at n, right? So that's 1. We'll have k plus 1. And so if I'm not mistaken, this is j. Yes, everything's good. And now the only problem is this curve valid subsets, we never update it, right? Because I want, after the end of this loop, I want the curve valid subsets to be updated, right? So before this loop, I will have to create a next curve valid subsets list. And whenever I have something that is valid, I will just say curve valid subsets dot append new mask. And after the loop, I'll just say curve valid subsets equals next curve valid subsets. And now we can try to run. There's probably typos in there. We do have mistakes because the test cases don't work. Yeah, so the first mistake is this one. We want to get in there only if the j bit mask is not in mask. So this is a if not j in the mask. So no, if j is not in the subset, then we can add it, right? So that's the first mistake. And I think, yeah, that's the second mistake. We never append to this list. So that's just what it should be. And now the test cases work. So I'm not sure how it actually work, but we can try to submit. And then we hit memory limit exceeded. And the reason why we hit this MLE is because in the next current valid subsets, we have duplicates, right? It is possible if we have, let's draw. If we look at our example, or maybe let's make a new graph. If I have a graph with 0, 4, 7, right? This is node 0, node 1, node 2. I can start when k equals 1, so I already have something. I can create 0, 1, but I can create it starting from 0 and adding 1, or starting from 1 and then adding 0. Right? There's two ways for me to arrive at this new mask. And those two ways are valid masks that were in my previous valid masks subset variable, right? So instead of a list for the next, I forgot how I called it. Instead of a list for the next curve valid subsets, we want to use a hash set so that we don't have those duplicates. So if we do this and add here, this should make, actually we don't need to make a list here, we can just use a set here and use this here, and then now nothing changed in the correctness, but we are using a lot less memory. And also time, by the way. And so this is still too slow, and the reason why is because we're doing a lot of hashing. And hashing, even though it's big of one, is quite expensive. And so we have a way of not using any hashing and using lists instead. And the idea is we'll just go back to using lists and using lists because there's no hashing in lists, so it's a lot faster. But we also don't want the duplicates, so the idea will be that we will only append if dp new mask is -1. It means we had never seen it before, so we can append it because it's the first time. If it's not -1, we will update it if we find a better way to arrive at this state, but we don't have to try to append it because we know we've already appended it. So that will hopefully hugely accelerate our submission, make our submission faster. And this works. For the complexity, this is a bit tricky to analyze. This will take 2 to the power of n space and 2 to the power of n time, so that's quite easy. This is very, very fast because it's like n squared, because there's very few nodes and edges. And this 2 for loops here will be bounded by 2 to the power of n, because if we look at all the valid subsets of size k for all k, then this can't be more than the total number of subsets, which is 2 to the power of n. So this is 2 to the power of n, and for each of those we do a linear time operation. Well, there might be a log here, but because we're bounded by 32 bits, 64, well actually 32 bits, that doesn't count. This is n, big O of n here, so in total the complexity will be big O of 2 to the power of n times n. And yeah, that's it. Right. Hopefully that was clear. Have a good one.